Okay, sorry for being late. Now, Italians are always late, so just blame on me. So, but that's... okay, so no problem then. Oh, perfect, okay. So, okay, so since we have been late for this morning, so I'm not going to tell you about this. This will start talking tomorrow, so if you want to... And so I just tell you a bit about this, statistics. Some of you, I understand, already know everything. So you can yawn. I won't say anything. But some of you do not. So, well, this, in some sense, I'm going quickly over this because Ran has nicely introduced. Why should we actually bother at all? Well, of course, it's a part of a daily activity or nocturnal in an animal. And then eventually, this is the whole reason why we are here. We want to have a sort of quantitative grip on representing how animals move because it's fundamental. So that's why eventually we want to understand behavior with some numbers. So, and then I would say that there is also another important aspect. If you parameterize your animal the way they move, they are important for a variety of processes, epidemics, disease spreads, food encounter, and so reproduction and so on. So that's why we do it. So what are these? I think I'll probably skip the animal navigation. What I'm going to tell you, I'm going to try to introduce you to then tomorrow probability density function, what we mean by stochastic and deterministic. Some of you might already know, but just because Ran made a comment before, it's probably useful that I tell you. And then we'll just go in with some math, trying to see what we typically try to extract from trajectories of animals, which are displacement, distance, turning angle distribution. So that part I won't touch it. Well, so I'll go briefly over this. Well, how do they navigate? Well, they use different sensory modalities, and we have heard Ran gave a nice representation. They are typically people tend to talk about egocentric spatial localizations. In order to navigate, you need to understand where you are before you decide what to do. No? So there is, which is called path. I think you called group navigation on type 1 or 2. There was type 2, yeah. So it's and so this is sometimes it's called also egocentric, and so this, some insects do that. Insects and when you measure distance from nest, for example. Then there is also something that's called allocentric. And I mean, you're distinguishing between two, but when you have external beacons in some sense. And then there is the one that Ran called the type 3. It's a sort of allocentric still. And when you actually have cognitive maps, it's still, it's not clear. Apparently humans might have it. It's hard to test it because you would need to kind of find the right neurons to do that. But this is some hypothesis which is out there. So, and the way why I'm telling you about this, and that's why we are interested in calculating distance and turning angles, is because in order to eventually navigate, irrespective of how they have, irrespective of their sensory modalities, most of them, what they do, they measure, they need to quantify distances and angles. Because irrespective of if you have a cognitive map or not, eventually then you want to go straight and turn. So this is a key to understand. And so what they do, so we try to characterize in the simplest way possible with straight line and turning line, and turning angle, sorry. So, you have an animal that, typically is what you have the so-called fixes, and then this is, depending if you measure like, so let's measure like this. This is your turning angle. These are the fixes. Now, there is a whole aspect of, if you characterize, and you can clearly see here, it depends on the sampling rate. And unfortunately, there won't be time to discuss about ways of trying to deal with that, since, part of my chore here is to try to present you with the more sophisticated mathematical techniques. But we can discuss in private, as I say, after the lecture. So we'll assume that the resolution will be high enough so that we have a good representation of the way they move, because you have enough sampling. So, well, just to mention what are the factors that determine the statistics? Many. Predator-avoidant distribution of resources. Well, you heard me today about social interactions. And spatial confinement is another aspect, which doesn't have to be because of the others. It could be just orography of the terrain. So now, this is important because eventually, again, my aim is to make you familiar with probability function. And so I want to just stress a bit what do I mean by stochastic or deterministic process in the context of trajectories of animals. Well, so, and it turns out to be a useful framework to characterize animal movement. It turns out to be when you describe this in terms of degree of randomness, or if you want, degree of persistence. So, well, the simplest way of thinking about the difference, I just give you two examples which make it clear. Everybody knows that coin flipping is a random process. So the outcome is always unknown. And we all agree that, well, unless you're in the UK, you don't see the sun. Oh, they're filming it. OK, bad. So, so the Earth's rotation is a deterministic process. We all know that it's always going to come back. Okay, there is some aspect of the rotation which maybe we don't fully know ourselves, but astronomers know very well. So that's for sure a deterministic process. What happens in terms of trajectories? So, well, I mentioned before, so you have fixes, and you have, well, that's the trajectory. So it's a connection between observation points of an animal in space over time. So the corresponding of a deterministic process in the concept of a trajectory is what I would define a ballistic trajectory. And it has a maximum degree of persistence. So something that keeps moving without ever changing. So that's the corresponding of deterministic. So, I mean, I just mentioned to you wave propagation. The wave has a certain, even if it's not just an animal, single point that you represent, it just has, it's an entire feature, but it keeps moving without ever changing shape, unless it's dissipating energy. But so that's another ballistic movement. So if you, in that respect, if you want to represent some trajectories, then I think I have a couple of graphs. So that's it. So on XY plot, that's clearly a ballistic movement, at least in this range. The animal has been ballistic there. Now, you can have some noise. And this is, you might call, I mean, it's not an important definition, but you might call this is quasi-deterministic. Because, somehow you perceive there is a sort of persistence. So there is, as if there is an aim. But there is some noise associated with it. So the trick becomes how you actually quantify that kind of noise. So now if I draw you some random trajectories, I mean, let's say more random than the one that you've seen before. So I'm going to give you some names. Well, I mean, we studied that in detail. But so this is a classical Brownian trajectories, the green one, which Ryan introduced very nicely, talking about Brown, who invented the name. So if you have continuous space, continuous time, then and you draw this in some way from some distribution of turning angles and displacement distances, then you get these trajectories. And it's Brownian is completely random. So every step, the angle that you pick is just between minus 180 and 180 degrees. Here, on the other hand, you can see some persistence, although because there is some sort of direction of movement. But you see it's very noisy. So that's a classical example of a correlated random walk. And this is those that people nowadays love so much, which is the Levy walk. So you have choice of angles which are random, but then you have some cases you have this long displacement. And so, if you look at these, it's clearly they're very, very different, the three of them. And if you have such trajectories, in general, what you want to do is you want to construct distribution functions, so creating histograms of, and we are going to discuss about this, of the distance traveled without turning and the choice of turning angles. Now, why do you do that? Well, simply because if you actually want to understand and explain to me, oh, I've seen these trajectories, which is zigzagging like this and like that, I will understand a thing. So you need to quantify this zigzagging. And so you create the distribution, and then you know, if you want, you give names to this distribution, or you quantify this distribution from some modeling understanding. And this is the purpose of this, whatever, 45, 50 minutes lectures. So now, before we actually do a little bit of math, in general, Ran said that I was going to tell you about segmentation. I'm not, but since he mentioned, I'm going to mention a couple of things, which again, if you have a trajectory of animals, you indeed have a collection of position over time, with respect to some reference point. There is always some origin with which you refer to. And so what you get, well, this is just, I shouldn't say random, but this is just a pickup situation where you have maybe an animal which is being observed at 1.5 kilometers along one axis and 3 kilometers along another axis. There was some origin at, where the observation at the clock was indicating 135 minutes. And then after some times, it was found at 2 kilometers, 5 kilometers on the other axis at 2.5. So these are the data that you typically get from any kind of data of this type. So what you do is, of course, what you can do blindly is you take all your data and you create this distribution of displacement, distance, and turning angles. But that would be really not doing something, not doing something intelligently, because you have, of course, you have biological information and the terrain over which this animal was moving. So segmentation is the first step to trying to understand. I try to characterize this animal's trajectories. So if you know that it's migrating or it's foraging and so on, so then you take that chunk of data and you create distribution of that part, and then when it's migrating, you do another type of selection of data and so on. So then if you have this segment, then indeed you reconstruct the distribution. And then once you have reconstructed, you plot this distribution, then you can talk about, as I said, rather than zigzagging of the trajectories in a colloquial way, you just talk about how you fit this distribution. So with just numbers, which represent maybe the shape near the origin, near the peak, or the shape towards the tails, and so on and so forth. Now, as you clearly understand, there is a lot of complication in doing this, and a lot of times you have to optimize this point based on what you actually have here. So sorry, Rand, that I'm not going to talk about segmentation, but it's a pretty complicated business, and solutions are needed. I can provide you one today, probably not even tomorrow, but so we'll talk about something. Also, this in private. So whenever I say in private means I don't know, so we can talk later on. Okay. So now let's do a little bit of math. So I know with Hanjo probably this in a half an hour or so we'll do some exercise, and I know that it's going to do exercise in R, but probably also in MATLAB you have routines maybe that allow you automatically, given x, y coordinates and time, to automatically create turning angle distribution and displacement distance on. But I thought that is useful for educational purposes to know exactly what those routines do. And so that's what we do, a little bit of math. It's very simple. It's calculus based. So, but anyway, stop me if there's something you don't understand. Oh, so there's something missing there in the figure. Yeah, so as I said, we imagine you have 3 points which represent your trajectories, and x, I, y, I, and so on. So there is some origin here which gives you these coordinates. You have your distance A. We all know Pythagorean theorem. No? That's how you compute the distances. So those values, if you have, if you'd have to plot them, so what you do, you just let's say this is this is observation number for one trajectories, then it would be data 1, then you would plot the value of dA, whatever that value is, you plot it over here, no? And then the value dB, it seems exactly equal. So let's suppose it's a bit larger. Then you would have observation number 2. Then you plot it here, and so on. So these are just positive because it's distances. And so and to create a distribution out of this, we all know how to do it, no? So essentially what you do, you have to bin the data. Bin is, sometimes people tell me that I should not use the term bin. Do you understand? Anyway, bin, it means that you decide how coarse are your selection of values of data points, and then the number of those that are inside here or there, well, OK, whatever number, and there. So there will be a number there. So they represent the value on your histograms. So then imagine here you had 5 of these. So then you have your histograms, which is the frequency here. And then that would be, so this was 0. So there was, the first bin was, let's say, 0 to 1 kilometer. No? This was from 1 to 2 kilometers. So 2, 3, 4. So this is the 3, and this is the 4. 0 to 1, 1 to 2, 2 to 3, 3 to 4. So here you would have a value of 5. And so then here, let's say there were 3, so you would have a value of 3, and so on. So this is actually what you do when you create these histograms. Now, for the turning angle, which is indeed this, so it's the angle with respect to if you were going to go straight, you want to see this angle, and it could be this way or the other way. And of course, it's 0. You just keep going straight. And well, the choice of being positive or negative is up to you. So you want to measure from 0 to 180 this way, from 0 to minus 180 that way, or vice versa. It's up to you. So let's see. If we want to create this angle, this turning angle, so what you do, you have a reference point, which was somewhere on this plane. And then notice that this would represent this vector. If I imagine that you translate your reference point here, and then I have this vector. And with respect to this axis, which was my x-axis, I'll have an angle, which is your phi a. And then if you look at the other one, in order to compute these heading vectors with respect to that origin, I mean, you just as if you translate this one here, and now it's going to be your phi b. Now, this notation is such that I'm considering if I compute counterclockwise, it's positive, and if I compute it clockwise, it's negative. Again, but you can change it. And so the way you do it is that if you want to compute delta phi, which is the difference between phi b minus phi a, is indeed you have to compute the heading vectors first, and then you do the difference. And so what you see here, so if I write it for you, let's see, like this. So this is a rectangle. So there's a 90 degrees here. So if you want the d, what is called this one? This is dA is equal to the cos of phi a x. What do they call this one? This is x2 minus x1. Sorry, the other way around. So x2 minus x1 is equal to dA cos of phi a. So this is trigonometry, no? You have problems with this? You'll remember that, no? So it's a projection. If I have a rectangle triangle, the projection of this onto here, it's the cos of the angle in between. So no, in order to show you that phi a is, notice that I just invert this expression. So I have x2 minus x1 divided by dA. And dA we have just calculated in the previous slide with Pythagoras. And then this is actually the cos of phi a. So then I just do the inverse of this cos function, which is the arc cosine. And that's why you get that. I haven't finished, so let me just write. So I do the arc cosine here, so I get phi a. And here I do the arc cosine. And now, what are these for? Well, it depends on the sign here. Is it positive or negative? It depends how I decided to, as I said, no? It's a question of choice. So notice that if I want y2 minus y1, so this, and what is this quantity? It's just always of unit 1, but it is plus or minus, depending if y2 is larger than y1 or y2 is less than y1. Huh? You see, this is the modulus. So if I take the modulus of this entire thing, it's just 1. But the sign is positive, it's y2 is larger than y1 or not. So where was y2? So y2, with respect to that origin, suppose the origin was here, is larger than y1. So in this case, it would be positive, because I choose to make it positive when it's counterclockwise. So this is just to, I mean, depends on your convention. So you want that to be positive when you do counterclockwise, so you do this. And this is just because you want to convert radians into angles. Maybe you just think in radians, I don't know. So, and so that's why, well, you get what you get here. So similarly down here, just to see, you have x3 minus x2. Now you have this distance, which is dB. So it's here. x3 minus x2 is this one here. So if some of you may not see. And so again, the cos of that, x3 minus x2 is the cos of phi b multiplying the dB, which you see there. Now you do the arc cosine, so similar as I've done over there. And again, and then we follow the same convention, y3 minus y2 divided by the modulus. And of course, y3 now is going to be smaller than y2, so then it's going to be a negative number. And that's why here I've drawn it, it's a clockwise angle. Yeah.
You can calculate the azimuth to the north of the first trajectory and then subtract the new azimuth, no?
Yeah. 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 So now, in fact, when you do this, now when you do the difference, you have to be careful about one thing, which is this angle clearly can be between minus pi and pi, but also this one. So you don't want to get numbers which are larger than pi or minus pi. So you just have to be careful about that. And so when you calculate it, then you have to add or subtract 180 if it goes beyond. So yesterday I prepared this little graph, and I hope it's useful enough. Tell me yes, even if it's not true, OK? It was 2 in the morning. But so, this is one case where you have a phi a, which is, I think I just put it very close to 180, 178 probably I pick. And so this is phi b, which is minus 178. So, and if you do the difference, that's what you get. You get this huge angle. So in reality, the turning angle is just this. So then you have to, in this case, you have to subtract minus 180. So if those that are larger than 180, you subtract minus 180, and then you get this. If you have taken the convention phi b, counterclockwise, which is positive, and clockwise, which is negative, then you do the subtraction. That's what you follow here. And so you will have that clockwise, you'll have negative, and counterclockwise, you'll have positive. So it depends which. So that's what you have to do. I guess, can you raise your hands who already knew about these things? OK, enough.
Can you go back once?
Yes. I'm going to provide the PDF of this. So then There is a little exercise that I'm thinking about, unless I change my mind, but to do it. But we'll see. So this is exactly what you do when you use this code in whatever MATLAB, R, and so on. This is just nothing else. So I guess this is all Hengel needed you to know before he does any sort of exercise. Am I right?
Well, for some functions you don't really need background, but of course you need background information in order to interpret it and use
Okay.
it and know what's going on.
So, in other words, what you do, you remember you had the x, y, and t. You convert them to distances, heading vectors, and then if you want, turning angles. And notice that here you're missing one because you need 3 data points to get to one turning angle. And then, of course, you have your clock. You decide when it's a 0 of your time, and so you get all your delta t times between the first and the second observation, second and third, and so on and so forth. So this is what, headings, turning angles, displacements. So now, just to come back to give names to this distribution and essentially represent to some displacement distance and turning angle distribution, because I could just generate a very long trajectories and then do it myself. And so if you do it, this is what you see. So the Brownian case, now I haven't used, you see, this is bad. I haven't used bin large enough. But anyway, so essentially here what I'm trying to show you is that distance, and this is the frequency of occurrence on these data points. And this is the distribution of turning angles. Now, if I would have used a little bit coarser bins, then you would have seen something which is essential. You can already kind of guess, because the numbers here is 7 and 8, and this is 2. So if you make bin a little bit larger, then you are going to get something which is essentially uniform. So if I have to so Brownian walk has let's say this is turning angle. Oops, turning angle distribution, and this is displacement.
Maybe you call it step length.
Step length? Okay, you prefer? That's fine. It just you need to sampling to create the displacement. No, so that's great. Step length. The point is that step length then, yeah, it means that you have enough resolution, no? So step length, it means that you have enough resolution of the animal to say that this is actually the natural. But yeah, that's okay. It's just a question of nomenclature. So if you're used to step length, it's fine. But so the Brownian walk, what it has, it says this is uniform. And the distribution of step length is something that decays exponentially or even faster. It doesn't matter. So you have very short distance. You have, if you want, if you have an exponential, which is what looks like this, because I think I generated through an exponential. Then this is the mean. If you have an exponent, we all know, no? If you have e to the minus d over lambda, so the mean of this is lambda, no? Well, let's normalize it, but so the mean, so the average value is going to be somewhere here, so that's your mean. So, but if you have something which decays even faster, essentially still what you define a Brownian walker. So this is fast decaying, let's say. Yeah, exponential or faster. It could be, imagine Gaussian or I can invent functions which are even faster than e to the minus d to the n power. So, no, actually, if you start increasing the number n, then you have a sort of plateau for small values. So, exponential or yeah, some fast decay, which is, so let's put in parentheses exponential, let's say, so that you can have something which is decaying very fast, but up to value d is 1, no? So if I put function like this, e to the d to some power n, n is large, you get this kind of function, no? So you don't want to mess with this.
You know what exponentially bounded distribution is? Exponentially bounded? You heard about that? Maybe that's what actually
Yeah.
we want it to be exponentially bounded.
Yeah, but why do they call it bounded? I mean, it just is, yeah, okay. Exponential. Well, I mean, the exponential function.
It means that it can be as much as the exponential, but not less.
Oh, exponentially bounded in that sense. Okay, okay. So this is your exponential function, which is a function of the distance d. And this 1 over lambda is normalized. Remember, this d is a continuous variable. And it's normalized. It means that if you integrate, dd, so let me call it dist. So if I do the integral of d dist, so that's a differential, from 0 to infinity of that function, that's better be 1, eh? Otherwise, it's not a distribution. And then if you compute the mean, sorry, this is this. OK, let me not call it dist, otherwise you get confused. Let me call it module x. Module x. So some positive quantity. So now, if you want to compute the mean, this is what I wanted to just explain. What are moments of distribution? Do you know what are the moments of a distribution? I just see only a few faces which just do that.
You know, because you know them in different names.
Yeah, you probably know in different names. So if I have a distribution of the variable y, this is a distribution, which means it's normalized. So let's say this is dy is equal to 1, where omega is the range of values you can get. So a moment is simply over omega, it's y to some power. The mean is to power 1, no? So let me put n py dy. So this is nth moment of py. Nth because there was an n here. So the mean, when people average mean of that variable, is always when n is 1. So this morning I was talking about mean square displacement. It's a square, but it's a mean because you're averaging over, no? So if I put this y squared py dy, that's your second moment of distribution, and you can also call it the mean. In the case where y is the spatial variable, it's a mean square displacement, which is of interest in our context, no? So this morning, if some of you did not understand what the mean square displacement is, it's just simply that. So in principle, you take, all the distances traveled by this random walker, and then a given one, and then you plot, you create the distribution, and then you compute these moments, and that's what you get. Now, of course, what happens is that what you were seeing before is that my py was actually depending on time. So this you actually have something which is comma t, and therefore this one depends on t. Is it clear? So it's a parameter in this sense, t. And of course, better your output also depends on the parameter, no? Otherwise, something's wrong. No? So here, I'm not worried about time here. I'm just putting all the data together. Hmm? So I see. You have questions, or is it all clear? Now, so let's go. Unless you have a question, otherwise let me go back here. So now, so this is a Brownian walk. Now we have the other example, which was the blue one. And out of those data that I've generated, I'm creating this distribution of turning angles and the distance. I mean, the displacement or step length distribution. So notice this one is very similar. Huh? Yeah, it just happens to be, I mean, I just used two different random realization. I sampled the distribution, and so you get somehow different numbers, because I've sampled once, and this I sampled another occasion. But essentially, you see, if you look at the scales, 0 to 4, here goes to 5 probably. And again, you have an exponential. So if I write here now, oh, I haven't given a name. So let's, did I put the name? I didn't put the name. So let me put this one is exponential again. And then clearly, you see a big difference in the distribution of turning angles. So it's peaked around 0. Now, irrespective of how you try to course these bins, well, I mean, of course, if you pick one bin as large as 360, probably it becomes uniform. But it's clearly peaked around 0. So this is, let's say, peaked around 0. And so this is what you might call the correlated random walk. Yes?
Is it peaked around 0 only in your example, or is this a feature of this type of walk?
It is a feature.
If it does a circle, it's also correlated, but peaked around a different angle?
You mean if it does a circle?
Yeah, the walk is like this, right?
Yeah, I mean, if you do a circle, if you actually, you're doing something like this, you mean? That's what you're thinking?
Yeah, no,
yeah, I mean, the distribution is, yeah, remember that.
it's also this type of distribution, but not on 0, not different.
Yeah, I mean, you can put, let's say, I would define correlated random walk as peaked around 0 because it's a turning angle.
This is not a random walk.
So that one is clearly not a random walk because you are actually imposing, there is a sort of imposition here of, I mean, there is a heterogeneity in space that you're imposing this animal to do that. So you will never generate, I mean, the likelihood of generating from a correlated random walk distribution, I mean, if you take peak around 0 and then this one, to generate something like this, of course, there is a chance of generating, but you have to, I mean, you become, with a white hair and so on, and you will still not have found such a representation. So, I mean, it can happen. It could still be, because it has this feature of having turning angles which are peaked around 0, but the actual constraint is
That's
such.
another level of the covariance between.
Correct. It's if you want. If you want, you have. So I would just, let's stick to, for our little course, let's stick to correlated random walk, to being peaked around 0, and to have exponential distribution step length. So, okay, so this is a correlated random walk. Now, what time is it? Where are you? Oh, okay. And now the levy, the famigerated levy. So what does, and then you can see features of this. This is a levy walk. And now you can notice that I've used the same bin structure here and there. So they're very similar. So if I have a levy walker, so then this is uniform. And notice here, you have something that decays, but it's very peculiar the way it decays. Now, I haven't put a log plot here. I should have. But first of all, I just want to show you that the actual values here compared to here, no? The numbers here, 18, 20, and here you have a 70. So you have a high frequency of those, small displacement, step length. But notice the scale here. You have lots of wide gaps here, and you even have what this is probably 35. So it's even if you might think, oh, it's similar to this, it's decaying. Well, it's not at all. You know, here the values are very bunched up together, and here you have gaps, which just values of 5, 10, well, maybe not 10, but very large. But the frequency of occurrence of this is very small. So, in other words, you have a power law, and so one of the exercises is to construct these power law histograms in one of this afternoon. So, by the way, do you know how to construct power law histograms already? Oh, some of you know already. So the trick is that if you construct the histograms, if you follow that procedure that I was telling you before about the histograms, you have your data, and then you start bin of equal size, then what will happen is that you're going to get in trouble because there are areas where you have no bins whatsoever. And so this is, well, essentially you get this object. But then if you try to represent and try to fit quantities, you need to put in the log scale. And the log scale is you have a log binning. So as the data here are larger and larger, so the bin gets larger and larger. So that you have you put in some rather than having these gaps. So, but I mean, we'll just discuss, how to do it and so on. Well, if you know already, maybe just go and get a coffee. And I don't know. So, but anyway, so this is a power law. And I forgot with what I've generated, with what exponent. So, and if you want, the power law is such that, yeah, please.
Can it be a different non-exponentially bounded distribution like a stretch exponent, something like this?
Yeah, in the sense, well, it's not a Levy walk, it's something else. I wouldn't call it a Levy. The Levy walk, you take a Levy distribution, which is not even a power law, the Levy distribution. It's actually as, you define in Fourier space. But, if you create, so a Levy is a distribution which is versus distance, clearly starts at 1, and then we have some features. And then here, do you see? Yeah, is x to the minus some alpha. So it's a Levy alpha distribution. Oh, wait, this is x. Huh? Now, typically what people see in ecology is that, oh, yes, we just cut it down, and then you just draw a power law, and then you have to renormalize correctly. But the actual Levy walk is, Levy distribution is actually this. So you can talk about the Levy, or you can talk about a power law which has the same exponent as the corresponding Levy.
Yeah, but I'm asking if the step length is not distributed as a power law, but a different kind of distribution that has this fat tail.
Yeah, that's what I was.
A different kind of fat tail distribution. Is it also called Levy walk?
Yeah, that's what I'm saying. I was trying to say the actual Levy distribution is this distribution, which has you cannot really write in real space. You have to define in Fourier domain. But okay, if it just comes over your head, forget about it. But this is a real distribution. Now, if what you do to make it simple, rather than extracting number from a Levy distribution, which can be done, but it's a bit more complicated. I can give you a code if you want. You can extract from a power law, which is simply this curve, which has a cutoff here, that's called x min. And then it keeps on going. Now, as you do that, the coefficient onto this power law, that there is a coefficient that this allows you to make it normalizable. You have to calculate what it is. We'll do it. And that's what people tend to say, oh, I've used a Levy distribution. You haven't, but you've used a power law distribution, which has the same exponent of the corresponding Levy. This is just, it's not that important that what happens here from ecological processes. If you say the animal has moved for 0.10 to the minus 15 kilometers, is it important? Of course not. So this is just the definition. Do you understand? So that's. Any other question? So you all knew this, no? No, some say no. Okay.
Maybe you can complete the bias on the walk the definition.
Oh, the bias. Okay. So if you want, if you have bias when you mean there is a drift. When you have a drift. Yes. Yeah. So you on all of these, if you want, you can add. So remember that these are somehow histograms of movement data where there is some randomness. And the randomness has to do with the fact that you always extract values from a given distribution. Now, even if in this case, when you have something peaked around 0, you still extract values. Now, it's more likely to extract the 0, but you still extract values. So it's a random process. Now, when you have a bias, it means you have to think about intuitively that someone is blowing onto this animal, and then somehow it's going always in some direction. There is a deterministic aspect there, which is this flow of whatever fluid is moving into, that it pushes in a specific direction. So that's a bias. So but notice that is a deterministic aspect. There is no randomness there. So every step that it makes, these animals, there will be always a component with this vector associated with the strength of this field, which isn't going to be in that direction. So you superimpose to all these processes a bias. So, of course, if you can imagine, if I put a bias on the random walk here, then you will see that it may look like a correlated. And so how do you distinguish them? Well, I mean, you look at the data, and if you subtract the mean, when you look at some moments of the distribution, then you pick it up immediately. It's not that is a correlated rather than a biased random walk. So is it clear when I said when you subtract the mean? So for example, you would do this. You would have...
What would be affected? Both parameters would be affected?
No, if you subtract the mean and you have a biased random walk, then...
The mean of what? The bias?
The mean of the distance, yeah.
The distance.
So you would...
The angle would be affected and a bias?
No, if you do this... I'm sorry. So you subtract the mean, which has, you will see when we do the exercise, I don't know anymore when, but anyway, when we do the exercise tomorrow, but you will see that precisely how you get this subtraction that gives you the fluctuation of the x squared, and you have subtracted the mean of x. So, and you can do it on the date. So I'll tell you, there are always, remember that there is the difficulty here sometimes is that you can be formal, but then you want to know what to do on the computer, which is nothing, in some cases, nothing to do with each other. No, they have to do with each other, but it's not clear what you have to do. So if you have a formal explanation, then you always need, and if I don't provide it, just ask. You always need a computational explanation. Okay, fine, I understood. Now what? I have this data. What do I do? So there is that aspect, which is important. Otherwise, we just do math. So.
Maybe just to add at this stage that the bias random walker is actually artificially generating high correlation between the steps because these are predetermined directions, so there's not much difference between successive steps, and they will go very much around 0. Okay, the turning angle. But after a long time, the correlated random walk will turn back. Okay, and the mean position will be 0 after a long time. In the beginning, it will be like the displacement. It will increase with the square of time, but after a long time, it will be 0. Whereas bias random walk will continue in this bias, and you will get the mean location also some positive value. This is a clear distinction between these two. The blue line over there, when you see it for a fraction of time, it can generate it by these two very different processes, and it can look very much the same. But after a long time, you will be able to distinguish.
Yeah, or, you do that,
yeah.
and.
But that's in short time. It will not tell much.
Well, again, you're thinking about, because you're in ecology, you think about the data. I mean, formally it's correct. You would get, you subtract that automatically. Now, of course, the data, you might need a bit more time. But yeah, you're right. Yeah. Yes? OK, so I think for this part, I think I'm done. Well, there is the name. And I just put some animals which have been apparently, well, that I can tell you because I tested the data on the fox, so that's true. So apparently, that's been observed in different types of animals. And so anyway, this is, I told you before. OK, no, this is next time. So now, I guess Angel will do the exercise. And if you have any question, otherwise.
Okay. Maybe
yeah.
one more general thing is to distinguish between step length and displacement.
Oh, you want? OK, yeah, so please, run. I mean.
Yeah. So this is the location in T1. This is the location in T2, T3, T4. So these are the step lengths. These are the lengths of the step here, and here, and here. Okay? Displacement from the origin, okay, is at T2 is this one, okay? At T, it's this one. It's identical to the step length. Then here is the distance between the origin, right, and this point. And then here it's the distance between the origin and this point. So when we usually say displacement, we mean this.
Okay, I'm happy to use the argument.
Okay.
No, it's fine.
That's what I don't know. Also, you also use the same terminology. And
sure.
when you use step length, we mean this.
So when you say mean squared distance, distance or displacement? Displacement.
Maybe you can add this to the table and show how you expect the mean square displacement to.
Oh yes, good point. Good point. Oh yes, this is good point. Yeah. So the Ryan. So let me just put.
Maybe the mean location and the mean distance.
Displacement. So for this, okay, let's. Oh, for the one and walk, so this is T. So the area that an animal is exploring is linear in time. And if you want in 2D, it's 4 times the diffusion constant multiplying T. So D diffusion constant. This is 2D, 2D. And for the correlated, you have a transition. So it's quadratic initially because it's ballistic, and then it's linear in time later on. I don't know if you want me to write the full expression, but so let's say, yeah, let me say quadratic initially. So let's just say t squared small time and then linear. So t as long times. So you know why it's ballistic as, oh, OK. You see, the point is that I just draw it here again. So remember that you could see something doing like this. And so if I draw, I mean, a corresponding ballistic, which would just be like this, so it has the same features. But if you wait long enough, there will be some high turning angles that you pick that eventually make you, as Ran was telling you, make you eventually come back. So essentially, well, not exactly the origin, but you turn more. So then that features over time, you pick it up in the statistics. At short times, essentially, you don't have you're not extracting so many random turning angles, and most of them will be around 0. So you keep going. So essentially, you are ballistic. And the ballistic, it's like wave motion. So the distance you cover is t. It's linear in time. So the distance squared, which is your mean square displacement, therefore is squared of that. You follow? Too fast? So if you have wave motion, something that moves as a constant speed, so the distance is speed by time. So it's linear in time. The distance. Now, the mean square displacement is a distance squared. So, so it's going to be t squared. So ballistic is t squared. But if you wait long enough and you extract many of these random turning angles, eventually you start curving more and more. And so the features, so the diffusive features, which are the one where you have a mean square displacement, which is linear in time, will show up. And that's why you have a long time shift t. Now, the Levy depends. Yeah, so the Levy-Walker, I forgot now. So given, because the Levy is defined given a power alpha of the exponent. So now I don't want to say, so it's t to some, let me call beta exponent. No, it's no, you have to be careful. It's not alpha exponent. So, and now I don't remember exactly. It's a linear relation to the alpha. And I'll tell you tomorrow. I forgot. But it's beta larger than 1, and it depends on the alpha value. So the larger alpha, the larger is going to be beta. So, and I forgot. Well, the bias random walk, well, the bias is going to be if you don't do subtraction of the kind that I was showing you there. So you don't look at the fluctuation of the mean square displacement. So you're going to always to pick up a t squared because it keeps going. No? So it's ballistic. So the bias is ballistic.
Imagine that you have two itineraries that look exactly the same in terms of turning angles and distances, but one of them was made by a small beetle and another one was made by a fox. So how do you normalize the step by the size of the animal? Because it means something completely different to that.
Well, mathematically, they are going to be this. Whatever that work they produce, it's the same.
So wouldn't it be wise to normalize by the length of the animal or something?
Well, if you want, but the point is that you are interested, yeah. But this is to try to interpret biological. But to characterize it, if you give me the data of the beetle and you give me the data of the whale, let's say, and then I plot it, then only when I have to interpret, then if you want, I just know, OK, on this scale, what is the size of the animal? But otherwise, as you represent, creating this distribution of turning angles and distribution of, the only thing is that, remember, when you create this distribution of turning angles, you normalize to 1. So the area, so remember, when you do these histograms, so your histograms, before, when you generate them, you're going to have, whatever, Now, of course, the way I told you that you generate it, this is not normalized. Well, if you use MATLAB, then maybe there are some features that are normalized for you. But no, actually, not even in MATLAB. So now what you do, once you have created your histograms, now there is an area. And you better make all this area equal to 1. So that you normalize the probability function. You don't really normalize in terms of the size of the animal. So in that sense, I talk about the probability, and irrespective of the size of the animal. So I haven't really answered your question, but this is.
Since we are biologists, then we are not only interested in describing this, but then we will need the interpretation.
Correct. No, yes, but once you, I would produce this, I would normalize the area, and then I would talk about, about this distribution. Now, the raw data, what they have is that, surely the raw data will be that this, will have a bin of size, the size of this, even if the shape is the same as the one on the whale, it will be different, that bin. I'm sure it's going to be different. It cannot be the same, no? So that is when, you look at it, and so in doing this exercise, I don't think there is much there is no difference in analyzing, the beetle from the whale. You only know in the raw data that this one clearly is different, and if you look at this and you look at the one on the whale and you see a big bin there to make the same shape, then you say, oh, I understand why. So this, so that's, this, this is mathematical thing that I'm telling you. Of course, they are built to be general. So there is, so in that exercise, I don't think there is much to be learned. But on the raw data, of course, you have taken the data, you know exactly what has happened. So it's